Hello, we are back and we are now going to look at the last section of chapter 5, which is section 5.5, the substitution rule. So we have until now solved integral problems or integration problems, or we have evaluated definite integrals and indefinite integrals with simple functions or with the functions who we know are derivatives of certain functions. But we would like to expand our knowledge and try to see how can we integrate functions other than those. So for example, the first example I have here is tangent x. Now tangent, if you notice, is not a derivative of any function, so you cannot write the integral directly. So what do we do here is something called substitution rule. That's what we use. And how do we use it? Well, there are slightly different, actually in the indefinite integral it's simple, but with the definite integral there is a little bit extra work that we have to do, which is because of the limits. So I have steps for indefinite integral here first. So what we do, we start by choosing a function u, because we are going to use substitution. So we are going to substitute something with u. So what will we substitute? We are going to look in our expression or the integrand a function which is inside another function, or a function whose derivative is present in the integrand. So two things. So a function inside a function and its derivative, or maybe just a function whose derivative is present. So now if you look at tangent x, like in this form, we can't see anything. We can't see the derivative of tangent x, or we can't see anything else whose derivative is tangent x. So what we do here is we start by rewriting tangent x as sine x over cosine x. Okay, so integral sine x over cosine x. So now if you notice, so we have the sine x has its derivative cosine x, and the cosine x has its derivative negative sine x. So another thing which is very important is that the derivative present must be in the numerator, or must be being multiplied. In other words, the derivative must be being multiplied with the expression, not divided. So we cannot choose sine of x to be u, because the derivative then is dividing. So what we do is we say let u equals cosine of x, because cosine of x is a function whose derivative is negative sine of x. So we don't have a negative, but that's not a big issue. So we will take u to be cosine x, and that's what the first step is saying. And the second step is saying now find du. So du is going to be minus sine x dx. And this is something from Calc 1, if you recall. So now we are going to go back and substitute. So this becomes equals to, so sine x dx, if you notice, you can notice it like this, or you can actually find dx from here and go substitute, replace the dx by this expression. So the dx will be, so that you have sine x over u times minus du over sine x. So now sine x and sine x get cancelled. The negative sign can be pulled out, and inside you have 1 over u du. But what is 1 over u? The antiderivative of 1 over u, remember that is ln of absolute value of u, so that we get ln of absolute value of u plus a c. And so that is the step number 4 that we just did. We anti-differentiated, and now we have to replace the x back in u. So we get ln of absolute value, sorry, there was a negative sign, so minus ln of cosine of x absolute plus c. But notice here, so you can have this as your answer, or if you recall, the ln negative ln of x is actually ln of x to the negative 1, or ln of 1 over x. So if we move this negative sign up, inside here, then it becomes the power of cosine x, and this actually becomes ln of absolute value of secant x plus c. So that is another way of giving the answer. Okay, I hope you understood the steps. So let us try another function. The next example, integral of cosine of 1 minus 3x. Now again recall, if it was just cosine of x, you already know what the antiderivative is, negative sine x. But here we have cosine of something, and if you notice here, the function inside is a linear function. So whenever we have a linear function, we basically don't have to worry about its derivative because being multiplied, because the derivative of a linear function is always a number. So this is what we will take as u. So we say let u equal 1 minus 3x. Then du will be equal to minus 3 dx, or dx will be equal to minus du over 3. So now we go back and substitute, so we end up getting integral of cosine of u times negative du over 3. So the negative 1/3 can come out, and inside we have now cosine of u du, which we can easily differentiate. Actually, we can now consider the negative to be a part of cosine, or we could have left it inside, so that we can get in just sine of u plus c. And now go back, substitute, so we get 1 over 3 sine of 1 minus 3x plus c. So that is our answer. Okay, let's look at another example down here. So this is integral of x minus 2 over square root of x minus 1. Now again, this is something which kind of doesn't allow us to use our technique that we said directly, that try to find a function whose derivative is present. So you see x minus 2, derivative is 1, square root of x minus 1. Well, if we just think of the function inside the square root, which is x minus 1, the derivative is 1. So which one should we take as u? So actually there are two ways to solve this problem. So we would like to take the denominator to be u. So we say let u equals x minus 1. Now note here we are taking u to be x minus 1, not square root of x minus 1. But this gives us that x is equal to u plus 1. So note here. So that is an important step. So this is what we do here. So which means anywhere we have x, we can replace this by u. So now going back, we have to find du. So du will be just dx. And so now our integral changes to, so we have x minus 2 over square root of x minus 1 dx, which is actually now So x is u plus 1. So we get u plus 1 minus 2 in the numerator, whole divided by square root of u du. So which is can be simplified to u minus 1 over square root of u du. This now became something which we can handle, and so now we can divide each term by square root of u. So we end up getting square root of u minus 1 over square root of u du, or integral of u to the 1/2 minus u to the negative 1/2 du. So integrating, we end up getting u to the 3/2 over 3/2 minus u to the 1/2 over 1/2 plus c, or 2 over 3 u to the 3/2 minus 2 u to the 1/2 plus c. And now we go back, substitute u, which was x minus 1, so this is our answer. Another way of doing this problem is by actually using a technique which if your algebra is strong, then you can easily understand. So if you notice in the denominator we have square root of x minus 1, and recall that if I have x over square root of x, then I end up getting x. So if I have the same thing on the top and the square root of the thing in the bottom, we end up getting something like that. So that's what we are going to do. So we are going to split the numerator as x minus 1 over square root of x minus 1, which can be written as square root of x minus 1 over square root of, integral of x minus 1 over square root of x minus 1 minus integral of 1 over. So the first one gives us square root of x minus 1, and the second gives us 1 over square root of x minus 1. And now you can see we can do our substitution that let u equals x minus 1. So which implies du is dx, and our integral becomes u square root of u du minus integral of 1 over square root of u du, which is the same thing we just have, and we end up getting the same answer. So you can continue and finish this up. So this is how we do these problems. Okay, now what about if we have definite integrals? So in this case, we start the same way. We will find the function which we are going to substitute, which is inside probably another function and whose derivative is present, or derivative is being multiplied actually. Then we will find du, and at the same time we will find the limits for u. So we will, using the formula that we will have, we will use the place the value of x and find the value of u. And then the rest is kind of similar, and let's try to do an example here. So we have the first example, integral from 0 to pi over 2 cosine of x times, so this is being multiplied, remember, with this function, and this is sine of x. So this is like a composition of functions, so in function inside a function. So what is the inside function? The inside function is sine x, and you can see the derivative of sine x is cosine x, which is being multiplied out here, so that we can easily say let u equals sine x, then du will be equal to cosine of x dx. And now when x is 0, this gives u is sine of 0, which is 0. And when x is pi over 2, this implies u is sine of pi over 2, which is 1. So now we come back here and do our substitution. So the lower limit stays 0, the upper limit becomes 1. Now cosine x, so how are we going to replace the cosine x? So if you remember, in this case we actually don't need to replace the cosine x. Why? Because we know that the du has a cosine x. So you can think of this along with dx, that this is becoming du. So what this expression becomes is sine of u du. So now we anti-differentiate. So anti-differentiating sine of u, we get negative cosine of u. And if you recall, so we have a negative sign outside, and we will apply the fundamental theorem of calculus, and we can have negative cosine of 1 minus negative cosine of 0. So negative cosine of 1, we just leave it like that. Minus and minus plus, cosine of 0 is 1. So that is our answer. So 1 minus cosine of 1. So as I said before, leave the answer in exact form. Do not take out calculator and convert it into decimals. So this is how we do this problem. Okay, let's look at the next one. So we have x multiplied by e to the minus x square. So your first job is to realize or be able to see a function inside a function, and then the derivative of that being multiplied. So if you notice here, e to the minus x square, so this is a composition of function, and the inside function is the minus x square, and the derivative of minus x square will be minus 2x. Now we only have an x, and that is what is important. If the proper variable is present, we are okay. If the number is not present, that's fine, because numbers are easy to handle. Okay, so let's start. So what will we take as u? The u will be the x minus x square. Okay. Okay, so u is going to be, so we say let u equals minus x square. Then du will be equal to minus 2x dx. So dx will be equal to du over minus 2x. And at the same time, I will evaluate the limits. So when x is 0, you can see u will be equal to minus 0 square, so u 0. When x is, what is the value? 1. This implies u is negative 1. Okay, so now we go back and do the substitution back. So we have 0 to negative 1, x e to the u times negative du over 2x. So the x and x will get cancelled. The negative 1/2 can be pulled out. 0 to negative 1 e to the u du. And we have negative 1/2, and the antiderivative of e to the u is just e to the u, and then we have limits. So negative 1/2 times e to the minus 1 minus e to the 0 e to the minus 1 is 1 over e, or you can leave it as, so we have negative 1 half e to the minus 1 minus 1. Now we know that 1 is greater than e to the negative 1, so we can actually distribute this negative sign, and that can be your answer. Again, leave the answer in the exact form. Okay, last example. So now we have ln of t over t. So if you notice here, we don't have a composition of functions, so no function inside another function, but we have two functions. One is ln of t, and one is, you can think of it as t in the denominator, or you can think of it as ln of t times 1 over t. So remember, the derivative of ln of t is 1 over t, so which suggests actually that our u should be ln of t. Then du will be 1 over t dt, and limits. So when t is 1, this implies u is ln of 1, which is 0. When t is 2, u will be ln of 2. Okay, so now we come back here, do the substitution. So we have 0 to ln of 2, so u times du, because 1 over t dt is du. Or you can go back and do what I was doing before, find dt from here, t du, and replace the dt by that and cancel the t's. Okay, so this suggests that the antiderivative is u square over 2 from 0 to ln of 2. So replace the limits. We get ln of 2 whole square over 2 minus 0 over 2. So our answer is 1 over 2 ln of 2 whole square. So that is your answer. So note here, ln of 2 whole square is not 2 times ln of 2. So don't try to simplify that, leave it as it is. If we had ln of 2 square, the square was on 2, then that would be 2 times ln of 2, or we could have written it as ln of 4, but this is not ln of 4. So this is how you do the integration by using substitution.